thanks a lot, and thanks, of course, many thanks, of course, to the organizer for this invitation. It's the first time in India for me, so I'm very happy to be here. And so I'm a bit embarrassed because I think there will be a lot of repetitions in this talk. Okay, but so some said repetita iuvant. I hope it is true. I'm not so sure it is true, but anyway, I will be fast about some points. So as we have seen from the previous talk, this DFR quantum space-time model has some virtues. It has nice properties. This was formulated by Obriger, Federer, and Roberts in '95, based on observation coming from quantum mechanics and general relativity. And one can, as you have seen, develop quantum field theory on quantum space-time, and this theory has nice properties, as Andres has discussed, and I will also say something about further properties of quantum field theory on quantum space-time. And as also Andres has hinted at the end, it can also serve as a partial substitute of inflation in trying to solve the horizon problem, as we have shown in a paper with Sergio Dobliger and Nicola Pinamonti in 2013. So there are some reasons to study this quantum field theory on quantum space-time, on DFR quantum space-time. On the other hand, there is another subject which seems very, very interesting and that has been developed a lot in the last 20 years or so. And this subject is called perturbative algebraic quantum field theory. And this is a perturbative approach to the construction of interacting fields and interacting algebras of fields on ordinary commutative space-time. And it had a lot of interesting applications. It was used to show renormalizability of field theories on general Carvel space-times in a generally covariant framework. Then it was used to construct algebras of interacting observables, and then it was used to quantize gravity perturbatively, and and it was used to also apply quantum gravity to cosmology, and it was the result of the work of all these people, and also other people. I haven't listed anyone in this slide. So the aim of our work, I forgot to say at the beginning, I will report on a joint work with Sergio Dobliger and Nicola Pinamonti, which is going to appear hopefully by the end of the year or shortly after. So our aim was to try to build a bridge between these two approaches, so to try to apply this framework of perturbative algebraic quantum field theory, which is rather powerful, to renormalization, perturbation theory of quantum field theory on quantum space-time. So this is the aim. And we also wanted to study some cosmological consequences, if possible, of this approach. So that's the plan of the talk. I will briefly summarize quantum space-time, which was already done in many details by Andres, and quantum field theory in it. Then I will also summarize this perturbative approach to algebraic quantum field theory. And then I will show that it is possible to modify this perturbative algebraic quantum field theory to apply it to quantum field theory on quantum space-time. And then I will also recall some results that we had in the paper with Sergio Dobliger and Nicola Pinamonti, which motivate the simple cosmological application of this framework. So, okay, the motivations for quantum space-time are rather well known. So, if you combine quantum mechanics and general relativity, you find that if you want to localize energy in a region of radius r, this radius has to be at least of the order of 1 over the energy by Heisenberg principle. But if you want that this localization region is not hidden by a trapped surface, then you need that this radius is larger than the Schwarzschild radius associated to that energy, and this in generic units means that your localization region has to be at least of the order of the Planck length. That's the usual argument for non-commutativity of space-time. But so the original observation of Doppler and Roberts was that if you only localize one coordinate, then the trapped surface that prevents the observation of the localized event will not form, because you have because the energy density of the state will be zero, because if you only localize one coordinate, the energy can spread over all space. And so this must give rise to space-time uncertainty relation. So this is how they obtain this space-time uncertainty relation. So they consider the quantum state localized in a region which is characterized by these numbers delta q mu, which are the uncertainties. And if you can compute the energy density of this associated to this state, and you can use this energy density as a source in the linearized Einstein equation. You can solve the linearized Einstein equation, and you get some metric. And if you want to impose that the metric, of course, depends on the region in which you are localizing, and then you impose that the trapped surfaces will not form, otherwise you cannot receive signals from the region in which you are localizing, so the localization loses operational meaning. And then you get that in order for the trapped surface not to form, these space-time uncertainty relations have to be satisfied. And then you want to realize these space-time uncertainty relations by assuming that these delta q mu's are standard deviations of certain quantum operators, which satisfies suitable commutations relation, as for Heisenberg commutation uncertainty relations. And the quantum these commutations relations are those that also Andres has written, and they are these ones. In particular, the commutator between q nu and q nu is a central element of the algebra. And then, so what also Andres has discussed is that you can construct a non-commutative sister algebra E, which is generated in an appropriate sense by this quantum coordinates q mu, which is equipped with an action of the Poincare group. An automorphic action of there's an automorphic action of the Poincare group which acts on this sister algebra, which acts on the q mu's like that. This algebra has a non-trivial center which are functions on this manifold, which is two copies of the tangent bundle to the sphere. And it can also be written as the continuous functions vanishing at infinity on the spectrum of the center with values in the compact operators on a separable space. This summarizes what Andres has explained in detail. And then we have also seen this in Andres' talk. In irreducible representations, q mu can be written as a Lorentz transform of the Schrödinger's variables x1, x2, p1, and p2. And this as a consequence that there exist states of optimal localization which minimize the sum of the squares of the uncertainties, but the Euclidean sum of the squares of the uncertainty, because this quantity is just the sum of these squares, and so it's clear that the states which minimize this quantity are the translates of the harmonic oscillator Brownian states. These are x and p's in the Schrödinger representation, and this quantity is minimized precisely by the translates of the harmonic oscillator Brownian states. And so we call these states the optimally localized states. And they are characterized by a center of localization which gives this translation. And they are taught as the best approximation of points in quantum spacetime. In quantum spacetime, the best that you can do to localize a state is to use one of these. And then we can define free scalar field on Minkowski by von Neumann Moyal quantization. So this formula, you take the tensor product between the e to the I k q, which are the elements in the algebra, and the Fourier transform of the usual free scalar field on Minkowski. And formally, this is an element of the tensor product between the field algebra, the algebra of operators on Fock space, and the sister algebra of quantum spacetime. This field satisfies the Cohen-Gordon equation, where the derivatives are defined by differentiating phi after translating the q's by x times the identity. And of course, as Andres was discussing, at the end, locality is lost in this model, but you obtain it in the limit in which your space-time, your separations are large with respect to Planck length. In this precise sense, if you take two optimally localized states, omega x and omega y, localized around two different points, x and y, and you compute these partial traces of the free field with respect to these two states. So you put the states omega x and omega y on the E factor, and you leave the identity on the F factor, and you compute the commutator, you get something which falls off essentially as a Gaussian with lambda for large space-like separation of x and y. So when x and y are largely separated, this is essentially zero. But when they come together, then this becomes not zero, even if they are space-like. So you don't have strict locality, but only a locality in this approximate form. And then this was the free field. Then one wants to discuss the interactive field, and as also Andres was saying, there are several possibilities which are equivalent on your ordinary Minkowski spacetime, but which become inequivalent on quantum spacetime. The simplest approach is the so-called Newtonian approach, which is the one that I think Andres has taken. So you just define the interaction by the product in the algebra. Phi q is an element in this tensor product of the sister algebra of the quantum space-time with the field algebra, and you can define the power of phi q using the product in the algebra, and you can use this as the interaction Lagrangian using the traces that also Andres introduced. Then there's another approach in which which is the so-called Young-Feldman equation, which is a way of solving perturbatively the equations of motions. No, so you don't use Lagrangians or Hamiltonians, but just try to solve perturbatively the equations of motions. And this was studied in these two papers by these people, and I will not say much about that. And there is a third approach, which is a variant of the first one, in which you define the interaction by the so-called quantum big product, which is a different way of defining the nth power of the field. And this approach has nice properties. In particular, this yields an ultraviolet finite theory to all of that with an infrared cutoff. That's why I was asking about the infrared cutoff. And so I want to give some details about this, because this will be my main subject of interest in the following. So what is this quantum big product? The quantum big product is defined by a generalization of point splitting to quantum spacetime. How do you define a way to define for instance, the Wick square on ordinary Minkowski spacetime is to take the product of phi x, phi y at different points, subtract the expectation value, and then take the limit of when y goes to x, and this gives you the Wick square. This is on ordinary spacetime. On quantum spacetime, this limit y goes to x has to be performed in a way which is compatible with the spacetime uncertainty ratio. You cannot simply put y to x because it's not meaningful in quantum spacetime. And this is accomplished in the following way. you take the nth tensor power of the original algebra, of the algebra of quantum space-time, and you take the power as z moduli, where z, I remember, is the center of the algebra, and you define q mu j, which are the products 1, 1, 1, q mu at the jth position, and then again 1. And these are, so you have n copies of the quantum coordinates. And since we have taken the product as z moduli, the commutators, the big q's are the same in all the factors, can pass through the factors. So the commutators are 0 when j is different from k, are the common big q's when j is equal to k. Then you can introduce the center of mass and relative coordinates between these n coordinates. And again, because of this z moduli tensor product, you get that the center of mass commutes with the relative coordinates, and the relative coordinates again satisfy the same commutation relation, but just with a factor of 2 in front. And by this factorization, by the fact that these relative coordinates commute with the center of mass coordinate, this allows you to define conditional expectation from this tensor product to the original algebra, which is now the algebra generated by the center of mass, by evaluating optimally localized states on these relative coordinates. And evaluating the optimally localized states means that you make qj equal to qk in the best possible way on quantum space-time. And that's why this procedure is taught as a generalization of point splitting on ordinary Minkowski space. Using this map, defined in this way, one can define the quantum weak product by taking the ordinary product and evaluating then this conditional expectation. And the result is given by this formula. So you get this phi checker, the Fourier transform of the field, and you get this object which differs from the product on commutative space-time by this Gaussian factor here. So you get here something which goes to 0 as a Gaussian when lambda goes to 0. And then you use this as an interaction term in the Lagrangian. And when you do this, you find that this matrix that you get is equivalent to the S matrix of a non-local quantum field theory on commutative Minkowski with an interaction Hamiltonian which is given by this formula. So you see, you have the integral of the phi x1, phi xn with this kernel. So it's something which is non-local. And in this kernel you have a delta of x bar minus x, where the x bar is the center of mass coordinate. And x is the point t, where t is the one which is in the interaction Hamiltonian and spatial x. And as I said, this theory has the virtue of being ultraviolet finite, and then you can also formulate Feynman rules for this theory. And then, of course, you get modified Feynman rules. And an important point is that the time ordering has to be done with respect to the point x bar 0, so with respect to the time of the center of mass coordinate, and not with the times appearing in the fields phi x1, phi x7. And this is the reason why the theory that one gets in this way is unitary, because the time ordering is done with respect to this t, and so you have the usual Dyson expansion, where the time ordering is done with respect to the times appearing in the interaction Hamiltonian. And so the theory is manifestly unitary. But an essential difference is that the vertices of Feynman diagrams become fat in this theory. So, which means that Feynman diagram like this one, in ordinary quantum field theory, it becomes something like this. You have 4 points. Each vertex becomes 4 points. So these points are x1, x2, x3, x4. This will be y1, y2, y3, y4. And of course you can connect the fat vertices in all possible ways. And this also shows that, I have not written formula, but it is easy to see that then in this expansion, the propagator that one gets between the point xj and xk, one of these points, also depends on the center of mass coordinates of the corresponding fat vertices. So each fat vertex has an x bar associated to it, and the propagator depends not only on the coordinates of the points which are there, but also on their center of mass. So the resulting perturbation theory is unitary, as I said, but it's not easy to handle because of this fact. So if you want to pass to momentum space, you have complicated formulas, so it's not very easy to perform explicit calculation. So it was possible to show that it is ultraviolet finite at all orders with an infrared cutoff. But if you want to really compute diagrams, it's cumbersome. So we tried to look for a more manageable formulation, and in order to do that, we turned to this perturbative algebraic quantum field theory. So what is perturbative algebraic quantum field theory? I will give a short introduction. Okay, as I said, it was proposed by Brunetti, Fredenhagen, and Duch to construct perturbative algebras of observable or of fields for interacting theories. For instance, for a scalar field, but you can do it also for gauge fields. You can do it for much more general theories. So assume that you have a scalar field theory in which you have a free part and an interacting part, and it works in this way. So one first define in this theory we don't look at operators, but just as algebras of functionals on the configurations of the field. So one defines field configuration as smooth functions on space-time. So now for me now this can be done on a general global hyperbolic manifold, but for me M will be just R4, so just Minkowski. So configurations are smooth functions on Minkowski. And observables are certain functionals from configurations to complex numbers, which have the following property. So we require that the n functional derivative of this functional is a distribution of compact support. And then we also require a property about the wavefront set of this distribution. So the wavefront set is a subset of the tangent space or the cotangent space of the manifold, which tells you in which directions the distribution is singular. And so so it's a generalization of the singular support, which takes into account also the direction. It could be that at some point of the singular support there are directions in which the distribution is regular and directions in which it's singular, and that's the wavefront set. And we ask a certain property for the wavefront set. So in particular, we ask that the wavefront set of the nth functional derivative does not intersect the union of the nth Cartesian product of the forward and the backward like cone. So the points in the momenta in the wavefront set must not be all in the this point in the cotangent space of the nth Cartesian product of the manifold, and so it has n momenta, and the momenta must not be all in the forward or all in the backward like cone. And this functional, the reason for this requirement will be clear afterwards. This functional we call observables, and then we have the subset of local observables, which are the functionals such that the nth functional derivative is supported on the diagonal of the nth Cartesian product of the space. And also we consider regular observables, which are the observables such that the nth functional derivative is actually C infinity function of compact support. So examples, a functional like that in which you take fx1, fxn and integrate with a kernel which is C infinity function of compact support is regular. And instead, if you take something like that, so for instance, a typical interaction Lagrangian, this is local, but it's not regular, because if you compute the functional derivatives, they satisfy this property, so they cannot be, of course, regular functions. Of course, we are interested in local observables, but so regular observables have nicer properties, of course. So then we have this set of functions. Of course, in this set of functions we can multiply pointwise elements, but in this way we get a commutative algebra. But we want a non-commutative algebra because in the end we want this to be the algebra of interacting fields. So we deform the product in the pointwise product in this set of functionals by this formula. So M is the usual pointwise product, and we take the tensor product of two functions f and g, and we do which is so essentially saying the same thing as Moyal deformation, but which has not to be confused with Moyal. So now we are deforming the product in a space of functionals on functions of space-time, not the product of functions of space-time. And the deformation is done in the direction of the free field commutator function, the free field commutator, which is the difference between the retarded and advanced propagator. Why this? Because if then you take the commutator of phi x and phi y with respect to this product, which I denote by star with sub I over 2 delta, you get precisely the commutator. So this means that the algebra of regular functions equipped with this product is essentially isomorphic to the star algebra generated by the free quantum scalar field on Fock space. It has the same commutation relations, apart from the equations of motion. So it's an off-shell formalism. So the free field also satisfies the equation of motion. These phi do not satisfy the equation of motion, but of course you can quotient this algebra by the equation of motion, and you get something which is really isomorphic. Of course, these make sense also only in the sense of formal power series in general, but sometimes if you ask suitable bounds for the nth partial derivatives of this function, you can also turn this into a convergent series. For this product is actually very easy, but the interesting fact is that it can also be done for the S matrix, which I will introduce later. The S matrix will also be a formal power series, but in certain cases, as was shown by Dorothea Bans and Kaja Reichner, it can also be shown that it is convergent, it is a convergent power series. So, but now there comes a problem. As I said, we want we are interested in local functionals, but since the wavefront set of the commutator is contained in this set, which is, so you have the square of the manifold times the Cartesian product at the upper light cone with the lower light cone, or vice versa. And since instead, when you have f and g in general observables, their wavefront set, the wavefront set of their functional derivatives satisfy the condition that I wrote before, in general you cannot make sense of something like that. These are 4 distributions, and with these conditions on the wavefront set, you cannot make sense of the product. In general, this product is not well defined. So this means that since things like that appear in this expansion, this means that you cannot extend in general this product that I define to all the functionals, but only to, it's only confined to this regular functional. But as we have seen, the general interaction Lagrangian does not belong to the regular functionals. In order to circumvent this problem, the solution is the following: if instead of the causal propagator I consider the two-point function, its wavefront set is different. It doesn't have this part. It only has this part. So it is made in such a way that if x and y, p and q are in the wavefront set, p has to be in the forward light cone and q has to be in the backward light cone. And in this case, it is possible to form this product. This product is a well-defined distribution according to Ormander's criteria. And then it is possible to change the product from the product with the commutator to the product defined by the same formula, but where now we put the two-point function. And moreover, what is important is that with this new product, I get an algebra which is isomorphic to the original one, and isomorphism is given by this map, the map which sends f to this object. Again, we have an exponential of operators, and now here in the kernel is given by this combination of the two-point function and of the commutator, which is called the Adamant function. So in this way, what we get that we can pass from this algebra in which we have the product defined by the commutator to the algebra in which we have the product defined by the two-point function. And in this algebra, we can enlarge the product to all essentially to all functionals. Oh, sorry. And what is the interpretation of the elements of this algebra with this product? So alpha h to the minus 1 goes from here to here, and if you compute alpha h to the minus 1 of phi x phi y, you get this. You get phi x product with delta phi y minus the two-point function. So the objects here have to be taught when you look at them here as Vic-ordered expression of the field. So the passage from here to here is the passage from the algebra generated by the field to the algebra generated by the Vic-ordered expression of the field. So the product in here essentially summarizes the combinatorics of Vic theorem. So this is essentially a reformulation of Vic theorem in this algebraic frame. And then we have also to introduce time-ordered products in order to define the interaction. And time-ordered products are again defined again by the same deformation of the product with the Feynman propagator as a kernel. And these time-ordered products satisfy the causal factorization property, which also Andres has mentioned. So the fact that if you take the product of f and g to functionals such that the support of the functional f is earlier than the support of the functional g. The support of a functional is the union of all points such that for each neighbor of that point you find two functions supported in that neighbor such that the functional has different value on the respective functions. So if you have two functions such that the support of f can be separated from the support of g by a space-like Cauchy surface, this means that support of f is earlier than the support of g, then the time ordered product of f and g is the same as the product we defined by the two-point function. So, and of course, if the situation is reversed, you get the product in the reverse of this. So this is really the time ordered product with respect to this product delta plus. And this can be done for local functionals with disjoint supports. Otherwise, this formula does not make sense from the start. So if I start from local functions which don't have disjoint support, this formula does not make sense. But if I'm careful and first I start from function with disjoint support, then this expansion as a formal power series makes sense. And then I am left with the problem of extending this product to all possible local functionals. And this is the Epstein-Glaser renormalization procedure, inductive renormalization. So I can define inductively a map, a multilinear map from n tuples of functionals to functionals. I can define this by induction on n by requiring that all this map satisfy this causal factorization property and other requirements which are less important. So if someone gives me maps from 1 to n which satisfy causal factorization property and are defined for all local functionals, then the Epstein-Glaser machinery construct a map from which has n plus 1 entries. And in this way, you can construct all possible time-ordered products of local functionals. Of course, this extension is not unique, and the non-uniqueness is just the renormalization group freedom. So you pass from one prescription for defining this time-ordered products to another by renormalization group transformation. So the non-uniqueness is classified by the normalization conditions. And when one has defined these time-ordered products, one then extended to all local functional, then one can also define the S matrix. And the S matrix is given by the time-ordered exponential of the interaction with this alpha h3 minus 1, which is there in order to account for weak ordering. So you get this formula that the S matrix with an ER cutoff because local functionals are of this kind and have an ER cutoff built in. So this function g of x is the decoupling constant, but it is turned into a function which is a compact support in order to avoid infrared problems. And in this way, you get a formula for the S matrix. And in this construction, the S matrix is unitary in this algebra. So this product is one by construction. If the interaction is local. In general, if the interaction is only regular, you can also define this formula, but you don't get a unitary X matrix. And when you have defined the S matrix, you can also define the interacting fields by the so-called Bogoliubov prescription, which is given by this formula, which is just a version of the fact that the interacting field is obtained by multiplying on the left and on the right with the so you take the free field that you multiply on the left and on the right with the interacting time evolution. If you do it and expand the interacting time evolution in a series, you get this formula, and that's the Bogoliubov formula for the interacting field. And this holds for any local function. In this way, one gets the algebras of interacting fields in this way. So to each local function left, one associates its interacting field, and one can generate the algebra with the interacting theory by these objects with the product given by this product or by the product with the delta plus. So this is perturbative algebraic quantum field theory. Now, as I said, we wanted to apply this machinery to quantum space-time. So we take an interaction on quantum space-time which is defined by the quantum weak product that I explained before. And as I said, you get an effective interaction on commutative space-time, which is given the effective Lagrangian, and the effective interaction Lagrangian is given by this formula, which is more or less the same that I wrote before. Before was for the Newtonian, this is the Lagrangian. But then there's a problem if one wants to use the perturbative algebraic quantum field theory machinery directly. Why? Because if you do it, you get T products which make the time ordering with respect to the times which appear in the field. And as I said before, in this way you don't get a unitary theory. You get Feynman diagrams not computed with the Piaccitelli rules, but with the so-called field rules. And it is known that with the field rules you don't get a unitary theory. So if we blindly take the PAQFT setting and we apply it to this Lagrangian, we don't get a unitary theory, so it cannot be used. But luckily there is a way out, and the way out starts from this observation that in the limit in which g goes to 1, recall g was the infrared cutoff, so in the end we want that g goes to the constant function, so 1 or some constant, it's the same of course. The limit of this interaction Lagrangian is the same as the limit of this other interaction Lagrangian. And so we could use this instead of this, since in the end we are interested in the infrared cutoff, in the adiabatic limit. And if we use this, we can actually modify this perturbative algebraic quantum field theory in order to apply it to this theory. Why that? Because if I now define G lambda, which is this Gaussian kernel here, I can do the following. I can define a map iota lambda from the configurations to the configuration, which is simply convolution with this G lambda. And I can pull back this map to the observables in the obvious way. So R lambda of f will be simply f evaluated at iota lambda phi. And if I define now this delta lambda, which is the double convolution of the ordinary causal propagator with this Gaussian, which is the same as saying that the Fourier transform is of the ordinary propagator, causal propagator is multiplied by a Gaussian with 1 over lambda. I can further deform the product in the algebra of regular functionals using delta lambda instead of delta. Before we had a product defined with delta, here now we have a product defined by delta lambda. And in this way we get that this map R lambda is a star homomorphism between the algebra of regular functions with this product, with the algebra of regular function with the original product defined by the causal propagator. And under this star homomorphism, the new interaction Lagrangian is mapped to this interaction Lagrangian, which is now local. So it's such that alpha h lambda of Li, where h lambda is defined in the same way as here with h here, it's now a local functional, because if you take alpha h lambda Li, you cancel this alpha minus 1 h lambda, you get a local functional. So instead of trying to use this algebra with this product, we can use this algebra with this product with a local interaction Lagrangian, and in this way we can do all the things that we have done before in the perturbative algebraic quantum field theory framework using this new product. So this means that, as before, I have now to deform also the product defined by the two-point function, and I deform it in the same way. So I pass from delta plus to delta plus lambda, which is again defined by the same convolution, or again defined by multiplying with this Gaussian in Fourier space. And again, R lambda is a star homomorphism between this new algebra with this new product and the original algebra with the original product delta plus. And one notice is also that this delta lambda is actually the commutator of the free field on quantum space-time with the localized with omega x and omega y, which I've written before. Before I said this commutator goes to 0 like a Gaussian, but its expression is precisely the delta lambda that I defined before, that I just defined. And delta plus lambda is just the two-point function of the free field on quantum space-time. So these two definitions from this point of view are very natural. And then I can also define the modified Feynman propagator, which is just the Feynman propagator with respect this delta lambda plus, delta lambda minus. So this defines a time-ordered product with respect to this new product delta lambda. And what is interesting is one gets a continuous bounded function instead of a singular function like the ordinary Feynman propagator, because we have smeared these functions with the Gaussians. Its Fourier transform can be computed easily, and it is given by this simple formula, which is not Lorentz covariant, of course, because G lambda is not Lorentz covariant here. x, absolute value of x stands for the Euclidean norm of x. And then one can use this modified Feynman propagator to define a new time-ordered product, which I denote by T lambda, which is the time-ordered product with respect to this product delta plus lambda. And in contrast to the case on ordinary Minkowski spacetime, this product is directly well-defined on all the algebra of functionals without any need for renormalization, just because of the boundedness of this function. So here the problem of turning on the Epstein-Glaser machinery to extend the definition of the time-ordered product from local functional with disjoint support to all local functional disappears completely. There's not a single problem. You can do it right away, and so you can directly define the S matrix. So H lambda, as I said, is just delta plus lambda minus 1 I over 2 delta lambda, and you define the S matrix by the same formula that we had before, but with the T lambda time-ordered product. And by construction, this S matrix is unitary in this algebra. So just because of its definition, this S matrix is unitary. And you can look at the perturbative expansion, the Feynman diagrams that you get from this S matrix, and you get the usual Feynman diagram. So the problem of fat vertices disappears. Now you get again the usual Feynman diagrams, and the propagators are modified by, instead of the usual Feynman propagators, you get the propagators modified by lambda. And then you can also define the Bogoliubov map, so the interacting observables, the interacting fields, and also what is interesting is that the map, the Bogoliubov map can also be inverted perturbatively. So one can define a new product on the algebra of F, which is the interacting product by this formula. So the interacting algebra can be directly defined by F with this interacting product, which is defined by pulling back the original, the delta lambda product with the Bogoliubov map. So one gets, I would say, satisfactory extension of perturbative algebraic quantum field theory to this to quantum spacetime simply by this observation that one can modify the Lagrangian. How much time? 5 minutes. Okay, maybe I skip this. I just wanted to say. So, as I said, in an older paper with Dobliger and Pinamonti, we tried to do the original DFR argument on a curved spacetime. The original DFR argument was on Minkowski. We tried to redo it on a curved spacetime, and we succeeded in the case of a spherically symmetric spacetime. And what we obtained, okay, forget about this. The main message is this one. So if you do it on a flat Friedman-Robertson-Walker spacetime, you get that for spherical localization, the limitation imposed by the principle of gravitational stability is that the moving coordinate R has to be larger than lambda over A. So you get an effective Planck length that diverges near the singularity because it behaves like 1 over A. And this is the reason why we could use this to give an alternative solution to the horizon problem. So this means that it is interesting to see what happens when lambda goes to infinity, because it has some, in cosmological situation you expect that lambda goes to infinity, lambda Planck effectively goes to infinity. And so that's why we want to study the lambda goes to infinity limit of the S matrix. And with this machinery, it's very easy to prove that to all perturbative orders, the S matrix goes to the simple the simple exponential of the interaction. So here B should be the interaction Lagrangian, sorry. also here, and that the interacting fields converge to the free fields, to the original free fields. So this means that when lambda goes to infinity, interactions disappear. And this is not surprising, of course, because when lambda goes to infinity, okay, the Gaussian kernel goes to 0, so it cancels everything. So we can interpret this by saying that near the Big Bang, interactions should disappear, and also correlations of free fields should diverge, because as we saw, correlations in quantum space-time have radius lambda. If lambda diverges, also correlations should diverge. So this seems to indicate that there should remain no degrees of freedom at initial times, because the correlations are infinite and there's no interaction. And also one obtains similar indications also in the Young-Fermat approach. One can do some computation in the Young-Fermat approach, and one also in that approach obtains the same result. And so one could speculate that this could provide an alternative solution to the initial condition problem. So the initial condition problem is the fact that you don't know what was the initial condition of the universe, and so you have to assume that inflation that uniformizes the universe and allows you to forget about the initial conditions. But that's another possibility. The possibility is that actually, if quantum space-time comes into play, there is no degrees of freedom, so no initial condition. Okay. So as a summary, I have tried to show that perturbative algebraic quantum field theory is an effective approach to the perturbative construction of interacting observables. And it can be modified to treat quantum field theory on quantum space-time, or a suitable class of non-local quantum field theory on ordinary space-time. Actually, we applied it to a non-local quantum field theory on ordinary space-time. And in this way, when one gets a unitary and ultraviolet finite S matrix without renormalization, with an infrared cutoff. The infrared cutoff is still there. And in the lambda to infinity limit, the S matrix indicates that quantum field theory and quantum space-time has 0 degrees of freedom at the initial singularity. Of course, there are a lot of things that one should do. There are indications that the perturbative series for the S matrix is also Borel summable in 4 dimensions, which I think it would be an interesting result on its own. So we plan to address this problem in the future. And also, as I mentioned, perturbative algebraic quantum field theory was formulated actually for treating quantum field theory on curved space-time, and one gets in this way generally covariant interacting theory. So it is tempting to try to do the same for quantum field theory on curved quantum space-time. So in order to get some generally covariant quantum field theory on curved space-time, but this is more far to be reached. And about this fact of the initial conditions, it could actually be that initial conditions, even if everything goes to 0 in the lambda to infinity limit, so when t goes to 0, it could be the initial conditions are replaced by different asymptotics of the theory when lambda goes to infinity. So it could also be that even if we have this result, this does not solve completely the initial condition problem. Thanks a lot.
Okay, thank you very much.